Good afternoon, everyone. My name is Hani Esmaeelzadeh, and I'm here with my colleague Amr Alanwar from UCLA. Today, we would like to talk about our research on power-efficient localization and time synchronization. Internet of Things is a multi-billion-dollar market, which is expected to deeply affect our industry as well as our daily life. It is anticipated that there will be about 21 billion connected IoT devices by the year 2020. This will dramatically increase the amount of power consumption. Also, as essential services, time synchronization and localization are required between many IoT devices. So time to plan for future has arrived. As pointed out, power consumption is a huge concern in IoT applications. One effective way to decrease power consumption is by duty cycling as much power-hungry circuitry as possible. However, in order to achieve efficient duty cycling, there are a couple of points to consider, such as how often the system must be duty cycled, or what happens to the accuracy of performed services as the system goes into sleep. Blindly duty cycling a system without having a real-time notion of its accuracy could degrade the performance. Furthermore, in real-life, systems do not wake up quickly. They have a startup time which is usually long and unpredicted. This degrades the accuracy of time synchronization. As a result, the estimated location will be off. The long startup time also increases average power consumption. So our research called PLoTS is an attempt to address the mentioned challenges in a unified fashion. We will go over more details of PLoTS in the following slides. Time, location, and power consumption are closely tied together for the following reason. Locationing is usually done by measuring the time of flight of a radio frequency signal. So an accurate measure of time is necessary for accurate localization. One way to achieve accurate timing is by using local stable clock sources. The cost is high power consumption of stable clock sources. An alternative way of achieving high accurate timing is by transferring and exchanging synchronizing messages with a master node, which have access to a very stable clock. This also comes with a high power cost due to the extra communication overhead. For instance, GPS, in order to find location, it requires 10 nanosecond time synchronization accuracy, which is achieved in these devices through synchronizing with satellites that have access to very accurate but high-power atomic clocks. So overall, you could see time, location, and power consumption are highly and heavily intertwined. Usually, localization, time synchronization, and power consumption are treated separately. However, as pointed out, there is a great deal of interaction between these domains. So we propose to study these interactions and exploit them toward developing an IoT device which is capable of performing power-efficient localization and time synchronization. We call our technique PLoTS. The basic idea behind PLoTS is to make use of Kalman filter as an application-specific measure of performance. Kalman filter takes distances between nodes and local time at each node, and it generates locations and global time estimates along with the covariance matrix. The covariance matrix is an indication of the correctness of the estimates. And we propose to use this covariance matrix to efficiently duty cycle the system without sacrificing its performance. Without a Kalman filter, there will be no notion of the accuracy of the system, and the system might as well go to sleep when it's not in a good shape. For instance, this plot here shows the covariance output of Kalman filter for localization. As you could see, this gives us enough information over time to know how to efficiently and adaptively duty cycle our system in real time in order to both satisfy the required performance and also decrease the power consumption. We will use it in conjunction with a fast startup technique that will further decrease the power consumption, and also it will improve the accuracy of the performed services, as we will discuss later. This block diagram conceptually shows how shows our proposed solution. The core of our system is a distributed Kalman filter, which is more robust compared to conventional Kalman filters, which are centralized solutions, and they are prone to single-point failure. So no fusion center is required, and each node relies on receiving information and measurement from its neighboring nodes. So overall, our system provides an efficient and adaptive duty cycling for time synchronization and localization with minimal power consumption, while maintaining a required performance, which is set by the user. However, there's still one problem remains to be solved, and that's the unpredicted and long startup behavior of electronic systems. As pointed out, startup time plays an important role in determining the performance of IoT devices, as it affects both power consumption and accuracy of the time synchronization and localization algorithms. So let's take a look at the startup behavior of oscillators. This plot shows the transient response of the oscillator during the startup, and as you could see, oscillation starts with a very small noise level, and then it exponentially builds up to a steady-state value. As we pointed out in the morning talk, the time constant of this exponential growth is proportional to the quality factor of the resonator over its oscillation frequency. Crystal oscillators are widely used in almost every electronic system. Their quality factor is in the range of hundreds of thousands. This enormous quality factor, as you would expect, makes them extremely slow at the startup. Furthermore, since the startup is a function of the initial amount of noise in the circuit, and the noise power is quite random, hence a startup time value would be very unpredicted. For example, a 10 megahertz crystal oscillator with a quality factor of 100,000 would take several milliseconds to fully turn on, which is orders of magnitude longer than the startup time of any other circuit blocks that we have on an electronic system. So you could see that the agility of the overall system is limited to the startup behavior of its crystal oscillator. To better show the impact of reference oscillator startup time on the average power consumption of the system, let's take a look at this example. This pie chart shows the distribution of average power consumption in a wireless transceiver. The crystal oscillator is assumed to have a 1 millisecond startup time. And as you could see, the oscillator by itself is taking up about a third of the average power of the system. On the other hand, if we decrease the startup time to 10 microseconds, you could see that the average power consumption drops by 30%. And overall, you could see that crystal oscillator startup time has a large impact on the overall power consumption of a system. Our proposed technique for improving the startup behavior of crystal oscillators is based on pre-energizing the crystal device within a very precise and narrow time window. The technique is shown briefly in this circuit diagram, where an on-chip ring oscillator is used as the injection signal. It will inject energy into the crystal device for the duration of T injection. If the injection is very short, then at the time of disengagement, there's not going to be enough energy in the resonator. And then after disengagement, it's left to the active circuitry around the oscillator to build up this energy to its steady-state value. And we know for a fact that the active circuit is extremely slow at doing this job. So we end up having a long startup time. Similarly, if we keep the two oscillators connected for too long, then excessive amount of energy is built up, and again, it takes a long time for the oscillator circuitry to adjust the energy level. However, if we disengage at a time where the amount of energy is equal to its steady-state value, there will be no transient, and we achieve minimal startup time. We did the math, and we can show that the optimal injection duration would follow this equation, where lambda is a chosen constant which could be precisely implemented, and delta omega SS is the frequency difference between the steady state frequency and resonance frequency, which has minimal variation thanks to the high stability of crystal oscillator. So overall, you could see that the optimal injection duration and hence the startup time now is a very constant and predictable number. For example, our 10 megahertz crystal oscillator, if we choose a lambda of 2 and a pooling factor of 1000 ppm, which are typical numbers, the optimal startup time following our equation becomes 8 microseconds, which is orders of magnitude smaller than the couple of millisecond startup time of the conventional crystal oscillators. So overall, you could see that our proposed technique reduces the startup time drastically and makes it also very predictable, which are essential ingredients toward having a power efficient and high accuracy localization and time synchronization. Next, my colleague Amr will present you with our initial results.
Thanks, Hani. In order to validate our idea, we have taken some steps toward our ultimate goal by providing some test bed which consists of mobile node and static node. For instance, this is our mobile node as a representation for IoT device. This is a crazy fly drone equipped by ultra-wideband radio for localization and time synchronization. For the static nodes on the other side, we have designed this circuit, which is Cortex M4 processor, and it's powered over Ethernet. And here is the node in the ceiling of our lab, and we have motion capture system capable of 0.5 millimeter localization error. We use ROS for visualization and control, as you see here. And we achieved 1 meter localization error and 2 microsecond time synchronization error as initial results. We are able also to do full autonomous flight based on accurate localization, and we will do position hold now. We will ask the crazy fly to hold in a position and push it, and it will return back to the same position based on accurate localization. Our initial result will appear in CICC and MobiHawk this year. Please visit our demo for more details and promising results. Our team has student expertise, resources, and student backgrounds. Our plan can be summarized in this table. While in fall and winter, I will work in developing new localization and time synchronization algorithm based on distributed Kalman filter. On the other hand, Hani will work on adding the startup technique to our test bed on the static nodes and mobile nodes. Also, in the spring, I will work on software packaging, and he will work on the power consumption analysis for the algorithms. And finally, we will integrate towards providing an IoT device which is capable of synchronization and localization and power efficient. Thanks.